This first example problem has to do with the calculation of the radius of curvature. Okay, so we have a beam here, an overhanging beam, two supports. We have a shear diagram that's drawn right here, and then we have the bending moment diagram. The beam is a steel bar, 0.75 by 0.75 square inch. Is loaded as shown. Calculate the radius of curvature of the beam segment between the supports. Okay, so we're given the beam loaded as shown. We're given that it's steel. Because it's steel, our modulus of elasticity is 30 times 10 to the 6th psi. And we're going to find the radius of curvature. First thing I did here was I found what the I was. Moment of inertia, it's bh cubed divided by 12. In this case, that's 0.0264 inches to the fourth. To find radiuses of curvature, we're going to use equation 15.2. R equals EI over M. So all we need to do is know what the moment is. Per this diagram that was already given to us, we know that the moment is negative 2,700 pound-inches in the span that we're talking about from A to point B. Okay, so we'll just solve equation 2. We put in 30 times 10 to the 6 for E, 0.0264 for I, and then 2,700 pound-inches for M, and we get 293 or 24.4 feet. So that would be the curvature of the beam that's loaded as shown. Okay, so the next problem I want to talk about has to do with the formula solution for finding deflections. And this is 15.5, example 15.5. So we have a round, solid, simply supported steel shaft having a diameter of 50 millimeters, supports a concentrated load as shown. Compute the deflection under the load at point C. Okay, well, compute the deflection at the point of the load and at point C. Neglect the weight of the shaft, use the formula method. Okay, so given a round steel shaft, 50 millimeters in diameter, loaded as shown, find the beam deflection at the load point and at point C. Okay, so the first step is we're going to find our I, our moment of inertia from table 3, that's pi d to the 4th divided by 64. That's 307 times 10 to the 3rd millimeters to the 4th. And our modulus of elasticity is 207 times 10 to the 3rd megapascals. Now, as we talked about before, the units of megapascals is also the units of newtons per millimeter squared. I chose to write this modulus of elasticity in terms of newtons per millimeter squared just to make sure the units work out for me. Okay, so then, since we're using the formula deflection, we go to Appendix H and find the beam that looks like our problem beam is loaded. Okay, in which case it's a simple beam, and it's beam number 6 or case number 6 in the formulas in Appendix H. From this, our first one is that's this delta here. The delta is the deflection at the point of the load, which is PA squared times B squared divided by 3 divided by E divided by I divided by L. Okay, so in this particular case, A equals 400 millimeters, which is this 0.2 plus this 0.2. B is going to equal 200 millimeters. And then the overall length is this 600 millimeters. So now I have everything I need. So I'm going to substitute everything in here, and I get a deflection of 0.168 millimeters for deflection at D. Now they want the deflection at point C. Now for the deflection at point C, I'm going to use this equation here, delta x. When x is greater than a, the deflection at point x, okay, in this case what I'm going to do is I'm going to put in x equals 200 millimeters because that's where point C is. And then I'm going to use this equation right here. This is the deflection at x. Okay, so what we'll do is we'll use this formula right here, and we'll substitute in x and b and l and e and I and p and everything else. Okay, so when we substitute that in and work out the equation, we end up with 0.147 millimeters. So that is an example of how to use the formulas to solve a deflection problem. Pretty easy, huh? Okay, next, I want to introduce a concept here. This is a formula problem again, but I want to introduce a concept of superposition. Okay, so we have a 4-inch nominal diameter standard weight steel pipe that's used as a cantilever beam, projecting 12 feet from the fixed end. Compute the deflection at the free end due to the two loads. Neglect the weight of the beam. Okay, so given 4-inch diameter standard weight steel pipe loaded as shown, L equals 12 feet, find the deflection at the free end. Okay, so you're going to need I, you're going to need E for all of these problems. So the first thing I'm going to do is I'm going to go into Appendix B, and I'm going to look up a 4-inch standard weight steel pipe, and I'm going to find that the moment of inertia is 6.82 inches to the fourth. And again, our E is 30 times 10 to the 6 psi for steel. We're going to use the superposition method. Okay, so what that's going to say is the total deflection at point A is equal to the sum of the deflections caused by first the point load at A and second of all by the second load. Okay, so the reason why we can do that in this particular case is that if we looked at Appendix H, Case 13 and Case 14, the maximum deflection for both of these cases is at the end of the beam. So it works for us. Okay, so the first thing we're going to do, we're going to go to Appendix H. We're going to look up Case 13. That's with the load at the point here. And we're going to write down the equation for the deflection. And we're going to solve the equation for the deflection. So, considering Case 13, and then this 200-pound load right here, this beam is going to deflect 0.304 inches. At the far end. Now, when we look at the second one, Case 14, that's considering a point load at the end of the beam. Okay, and we have a different equation for that. So when we solve that equation here, what we end up with is 0.93 inches. So therefore, by superposition, we add the deflection due to the point load and then the deflection due to the load at the end, and we get 1.278. The only thing I want to say about this problem is that my answer is different than what's in the textbook because they used a different I. Apparently in the 5th edition of this textbook, in Table B, there was a different I for a 4-inch diameter standard weight steel pipe. Okay, I'm going to stop this one here and talk about the next one in the next movie.